Where's Roger? Already used up that one. So I've run out of it.
Right, welcome everybody to October's meeting of the Astronomical Society of Frankston, and thank you for coming down in less than perfect weather conditions outside. My name is Skilton, for those of you that are new, and there are certainly a few new faces here tonight, and new members. Welcome to the Society. How the meetings usually run is we have a talk that will go for about the first 45 minutes to an hour. Then we break for a tea break in the room next door for up to about half an hour for a bit of a chat and a chinwag. And then we come back in here for various information sessions, which will then go until about somewhere between 10:15 and 10:30 as usual. Now, as our treasurer isn't here tonight, I need a volunteer who's going to act as treasurer on behalf of the Society, preferably a committee member, please. All right, I will nominate Jane. Also, reminders, members, please put your name tag on. It certainly helps members to know who you are. If you're a new member, John Cleverdon will have your name tag, and he's putting his hand in the air there. If you've recently joined and he's had enough time to prepare one, please pick up your name tag. The raffle, the dollar raffle, for those that are interested in participating, will come around, and it looks like the prizes tonight are Is There Life on Mars, Totality All About Eclipses, and a bottle of something probably from Ian Sullivan. And I'll hand around the idea, suggestion, question box and the viewing night roster as usual, please. Hand that round. If you can attend one of the viewing nights, please note your name down.
What's the other book there, please?
Eclipses, it's Totality. Right, congratulations to the following people. We have a 5-year milestone for Jane McConnell, and her reward is being treasurer for the night. And we have a few new arrivals. Presumably a lot of them have come from the Mars viewing nights. There's Roma and Tom McCulloch, Diana and Paul Vickers, Trevor Sweetman, Lou, Lisa, Stacey and Angie Mitsopoulos, and John, Nicola and Helen Mitsopoulos. A couple of families there. Welcome, 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 welcome. And during the tea break, one of our members will come and introduce you to some of the people, and I will nominate one of those members to actually be Peter, who's standing up over there making himself prime. Also, there's a What's On handout, which John Cleverdon has prepared, telling you everything that's coming up. If you haven't picked one up, they're in the little holder over there next to the doorway. Please help yourself to one of those if you haven't already collected it. During the tea break, the library will be open as usual. Andrew Thornton is not here tonight, so I guess Jane. Thank you, Jane.
Very popular.
Right. Well, since our last meeting, a few things have actually happened in the world. It's actually 12 months ago since the planet Quaoar was discovered, or arguably a very large asteroid outside the orbit of Pluto, and perhaps that might even come up as a question during the talk at some stage on the formation of the solar system, about those bodies out beyond Pluto. We had the first Chinese astronaut, or should I say taikonaut, I think was the term, gone up into orbit for 24 hours, making China the third nation to put a man into orbit, very much like the Russians for propaganda purposes. Our member and planetarium astronomer Tanya Heale had a baby boy last Monday. Dylan John Merchant, 8 pounds 10.7 ounces, and I don't know what that is in solar masses, because she don't actually tell me what that is. Since our last viewing night, we've had 3 public Mars viewing nights down at the Briars, which we capped off. They were on September 19 and 26 and October 3. And we had over about 220 people turn up for those, particularly everyone turning up on the very last one in particular. While the rest of Melbourne and the metropolitan area seemed to be under rain and cloud, down at the Briars at worst we had 30% cloud, so it was 70% clear, so they all got a very good view of Mars, even though it was raining where they actually lived, so they were very, very fortunate. Anything on members' nights, John?
Now that it's getting to spring, the weather's decided to start clearing up, and after about 5 months we had quite a good members' night back in late September. Just 5 of us turned up for that. Dave Girling, Bob Heale, Greg Walton, Roland Nabe and myself, and were there till quite late. Lovely clear sky, and my highlight was actually finding a 13th magnitude planetary nebula in my 6-inch scope, which was quite something for the Briars. But Dave was just telling me tonight he saw, I think, up to about 70 objects on that night. So it's proof that if you have a clear night around the new or first quarter moon, come along to a members' night on a weekend at the Briars and you'll have a great time. And also I've run off a few more flyers for the public nights at the Briars, so I'll leave those on the table over there if you want to pick one up later. And you can also download these and other flyers off the ASF's website as well. And also one last thing is that the Ken Bryant Scope Day that's planned for late next month will only go ahead now if someone is available to run it. There's David Girling has priority.
Okay, if anyone's interested in contributing to Scope Day and taking a leading role in that, please see John during the tea break. Right, astronomy classes, do you want to say anything on that, Ian?
Yes, unfortunately the Saturday the 25th of October was going to be the next one, but I've had a previous engagement now that I'm afraid I'll have to attend, which means I've put it off for a week. So Saturday, November the 1st is now the day, and I've told several people, and I put it on the e-Scorpius, but I'll have to check the people who came last time to make sure they know. Anybody else who's interested, we have to set these classes up so anybody new can join at any time, and there's got to be enough there for the people who've come before, so we've got to sort of work it through. You get notes and just follow up on what you can do, but it's basic sort of stuff, but it's theory, it's not practical work with telescopes. And so if you're interested at all, see me later tonight in advance, but remember it's Saturday, November the 1st, 1:30 to 4:30 at the Mount Eliza Community Hall.
Right, well without further ado, we'll begin the main item for the evening, and I'd like to invite along Dr. Andrew Prentice here, who's a reader in mathematics at Monash University, and indeed you may recognise the face from television from only a few weeks ago when the Galileo probe met its demise in Jupiter's atmosphere. And we've been very fortunate that Andrew has come along at Ian Sullivan's invitation, and I'd like you to show our appreciation of and anticipation of
Can everyone hear me? Probably don't need a microphone. That's not my first signal there.
Probably because you're getting in to switch it on.
Yes, I can turn on the mic. You want the projector on right now?
Oh, yeah, any time will do.
Yes, right.
You get a bit of backlight.
Right.
Well, good evening everyone, and it was a pleasure to come down here to Frankston. I have spoken, I think at least twice before to the Astronomical Society of Frankston. I think Ian, in fact, has been responsible for at least one of those earlier visits. visits when we used to meet over, I think, what's now, I think, a Monash campus, the nurses' establishment. It was a teaching college down just off the highway. And so I haven't been to this school before, but that shouldn't affect the talk. In fact, I've been in an unusual situation. I've been at Monash since 1972. I've survived all the various purges. Again, I was telling you about taking place there in the education department. And in fact, also, I think Ian was talking about significant birthdays. I just recently survived one of those, which is I think the age that's perhaps the most visible of all numbers. I've got through that barrier. And in fact, my parents are still alive. And yesterday they celebrated their 65th wedding anniversary. Quite amazing. I didn't think they'd last that distance. And anyway, so about 60 years ago, I sort of appeared on the scene. And in fact, I have a twin sister too. She's not. I've never been able to get her interested in astronomy. And nonetheless, it's always good to have a balance. My interest has always been in the solar system ever since I was a youngster. And of course, skies are we're a bit lucky out here in Australia that skies are so clear. And we were very lucky, as Ian reminded me last Monday night of last week, that we were witnessing that very rare sort of close occultation with Mars. So there's always something new happening in the evening skies. We're very lucky to be able to see that. And for a while, the planetary system had sort of become the backwater, but now I think it's becoming more, people are more interested in it now. We had transits. I think next year we've got the Venus making a transit, so I think public interest in astronomy has probably been as high as it ever has been. And I think these societies are playing a very valuable community role in telling the public what's happening. As I said, I've been in Monash since early 72, and I've maintained my interest in the solar system. I also, of course, we have fairly heavily involved in teaching there. But I've been very lucky that my sort of professional career more or less overlapped the program of sort of space exploration that NASA started in the very early 1970s. And I think we've had the Viking missions to Mars in 74, and I think there was also a probe that went to Mercury, or went fly past really. There will be another Mercury spacecraft called the Messenger, which we're probably going to get there for about 6 years. But there's still a lot to learn about the solar system, and though for a while everyone was looking outside the solar system, thinking there was nothing left to see, it's really just it's a trove of sort of treasures, apart from the beauties that it provides in the evening. So I was going to sort of give you an update on my ideas of how the solar system formed. My work sort of has always been regarded as sort of fairly controversial. I haven't sort of been run down with a great sort of avalanche of sort of supporters who sort of rushing up to get a signature or anything. Most of my professional colleagues tend to distance themselves a little bit from me actually at large meetings. But I was at the IAU in Sydney in July, and it really gave me an opportunity to, as the annual General Assembly of the International Astronomical Union, at least every 4 years, about 3 years. The last time they met was in 1973, so at that stage I think I just gave one short paper, but I took this last opportunity in July to actually, with the help of 2 students, we actually delivered 5 presentations and really made ourselves quite known. In fact, I even got a write-up one day, and the Congress had a daily newspaper, so that made my colleagues livid with envy over it all. They then, instead of distancing themselves, they suddenly wanted to be seen near me after the paper came out. So they were, in short, a very shallow bunch. Down here at Frankston, I'm sort of beyond the city limits, and I could probably maybe be more liberal in my assessments. But if you think I've crossed a boundary, then let me know.
Go for it.
was 2.25 million light years away, Andromeda. And I did mention at the end of the Galileo mission to Jupiter, I think, within our own solar system we've got a miniature planetary system, probably formed in the same way as the Sun formed our planets, and undoubtedly right throughout galaxies like that. There must be many, many other planetary systems just like ours. That doesn't necessarily mean that, they've got people at the same, on them at the same time we're on our sort of Earth. And there must be a whole lot of other factors that we aren't yet aware of that do control, how life forms. For example, I think if we didn't have Jupiter on the outskirts of the terrestrial world, I think Jupiter was actually responsible. Not only is it responsible today for shielding us from a lot of comets and things that come in from outside, Jupiter also in the beginning was being a bit of a spoiled sport in stopping the terrestrial planets growing, and almost certainly Mars should have been able to grow to the same size of the Earth, but it didn't. It only grew to a tenth or thereabouts. And even the Earth may not have perhaps grown as much as it could because of the effect of Jupiter. But had the Earth got a little larger and more massive, there would have been a greater amount of energy it would have liberated when it formed. And I think what we're just now appreciating, and certainly from the theory I've developed, when the Earth first formed, it had quite a lot of water, but in the process of the Earth accreting, it actually drove a lot of its water out into space, particularly when it formed the Moon. And had the Earth been even another, say, 5 or 10% more massive, it may have actually driven out all of its water, and we wouldn't be here today because we need water. And had the Earth been much smaller than it is today, we wouldn't have had all the other factors that are associated with retaining an atmosphere. So I think, although undoubtedly there must be many other planetary systems like ours out there in the cosmos, it probably only, probably it's only 1 in 10,000 that's able to support life. So that's probably why you haven't got a whole lot of aliens visiting us and things like that. And of course, beyond the many galaxies beyond there, as you get up to the whirlpool's about 60 million light years away. And then Hubble, of course, is now getting this galaxy even much further away again. This is sort of like a warped galaxy. And probably mainly dust there too. Perhaps star formation is sort of proceeding in a different way. And beyond that again, you get right out to the edge of the cosmos when the universe first formed. And looking back at those very distant galaxies, you're looking back at a time when they didn't have any heavy elements. So you wouldn't have been able to form planets anyway. So it's probably only in the last few billion years or so that you should be looking at stars that are as old as ours that would be likely to have planetary systems. So that's we've learned an awful lot about the Hubble telescope, which is one of the most valuable of NASA's instruments. I gave a lecture in May about what was called Olbers' paradox. Wilhelm Olbers was a German physician who had trouble sleeping, so at night he'd go out and do a lot of observing. One of the things he really worried about was why, he thought if the universe was infinite, then as you looked out into space, eventually the line of sight must eventually strike another star. And he sort of, although he didn't realise that the fact that the sky isn't a brilliant luminous globe all the way around, he didn't realise that the universe wasn't infinite. He didn't know why it was that the sky is quite dark at night. And it is, I suppose, really because the universe was formed 15 billion years ago. The light we see has come from 15 billion years ago at most. And if the universe was infinite, and if you had subscribed to what's called the steady state theory of the universe, then the sky would be brilliantly white, and astronomy wouldn't be much fun at all. So I think we're lucky that also the universe has just a finite age to appreciate the heavens. Well, I'll come back into our own solar system now and get back to my own subject that I'm really interested in, our own planets and how they formed. And of course, this Saturn was the most distant one known to the ancients. The planets Uranus and Neptune weren't discovered until more recent times. And I think about 1781 for Uranus and 1846 for Neptune. And Peter is right that he mentioned Quaoar being discovered a year ago. The planet Quaoar is actually at the next orbit out from Neptune. Neptune and Uranus are in nearly circular orbits, and if you go out in what's called the Tetius-Bode law of planetary distances, and one planet's roughly about 1.7 times further away from the Sun than the one before it, you'd actually come to the orbit of Quaoar. And about 3 or 4 years ago, Charles Morgan did tell me, he's doing a PhD with me, that he wouldn't be surprised, in fact, they did discover another large planet in a circular orbit out and out there. And in fact, that is in fact correct. And Charles has based his idea on this sort of modern Laplacian theory that I've been developing for the last 30 years. Because in the early 1970s, I did point out that the primitive Sun, when it first stabilized itself, would have had a radius of about 10,000 solar radii, and Quaoar, in fact, was found at about 9,400 or 9,300. So, in fact, the first planet that did form, the first gas ring, was out there at the orbit of Quaoar. And it is in a free circular orbit, and it can't be explained as being something that was thrown out from the orbit of Neptune, as, say, perhaps Pluto may have been. So I think there is, in fact, really growing observational support that the solar system really did form from a family of gas rings. And I'm going to sort of come back to that idea later on during the course of the evening, that in fact it was Laplace's nebula model that was responsible for the formation of the solar system. A lot of people are sort of reluctant to really accept that, and the Americans think you've got a great disk and things like that. But the disk theories have a lot of trouble explaining the solar system as it is, whereas the gas ring model seems to be able to cope with understanding pretty well all of these features. There is a lineup of all the planets. There's a site by a chap called Calvin Hamilton, I think. It's a very useful one, and it just shows how small the terrestrial planets are compared to the giants. And this is the Sun, of course, on the left, and a huge sort of globe. The mass about 2 by 10 to the 30 kilograms. So to answer Peter's other question, it would probably be about 5 by 10 to the 29 times more massive than someone's recent offspring. More massive. But yeah, so we get all our, we rely on the Sun to hold us in orbit. The planets are quite puny in comparison. Jupiter's only less than thousandths of the Sun. And these are drawn to size again. You can see the little Mercury there and how small it is compared to the so-called gas giants. So here's a note. Now we're getting really close. You can see these 4 worlds. So the main thing to know is about the 4 terrestrial planets. They're each completely different, not only in terms of size, but their composition is completely different. This is a radar image of Venus, and that's a very early sort of picture Viking one of Mercury. But each planet has got its own story to tell. It's made of different materials, and the only way that this could have come about is if each planet had more or less formed where it is today at its distance from the Sun, and there was a sort of a temperature gradient that went through the nebula. This slide here shows the densities of the planets with distance. Main thing to note here is how dense Mercury is. It's about 5.5 times denser than that of water, and almost twice that of its neighbours. And so Mercury is believed to contain a lot of iron, and it's quite an intriguing mystery as to how that came about. Thank you, Ian. I think it's an old slide, so it probably may be difficult to find it. Oh, very good.
That's about it.
Yes, and also would like you to focus on the detritus that's on the slide. Thank you, Ian. So here's the moon, of course. I believe it's the moon did form from the Earth, because if you go back to that previous slide, you'll see that the density of, there's the moon. The Earth is a little bit denser than it should be on a sort of steady scale coming down here. The Earth probably lost a lot of volatiles, not only water, but also a lot of, it vaporized a lot of the rocks in the process of forming the moon. The moon almost certainly did form from the Earth. as a natural process. I don't think it was a collision. About 5 or 6 years ago, collisions were considered to be very important. But a paper was published last year in America, or I think yes, there was a couple of chaps in America who were observationalists pointing out that they'd studied the composition of the Earth and all the other planets as well. And they had pointed out the implication was that there was not widespread mixing of the material in the inner solar system, from which each planet more or less received the overwhelming majority of its mass from narrow annuli, or basically that means rings, of course, which is the gas ring model. So there seems to be growing observational support that each planet did form in situ where it is and drew all its material where it is. And that can only come about if the planets have formed from gas rings, which is what I think Laplace had suggested 200 years ago, and which I've been trying to revise over the last 30 years with the so-called modern Laplacian theory. But the observational data now really moves against what's called the disk theory. This is Laplace's theory that the planets form from rings of gas that the sun had cast off in its infancy. The sun was once a big gas cloud, and as it grew smaller in size and it was spinning, it proceeded to spin more rapidly on its axis and eventually span so rapidly that the centrifugal force at the equator overcame the inward tug of gravity and a ring of gas was left behind. And Laplace conjectured that each planet formed one by one from these rings. And the theory was very conceptually sound and attractive, but it got thrown out because no one could understand why the cloud would throw off gas rings. It was thought more likely that you'd get a great disk. Now, if you could get a gas ring, and I might actually, Ian, I'll try using the focus button myself. I'll just go forward then. Thank you, Ian. And, yes, I can. That's fair enough. That's good. These gas rings are like slender tubes of gas going around the sun, and as the gas cools down, little grains settle out, and then they form a concentrated stream on the main orbit. And then later this stream draws together to form a planet. And according to the disk theories, everything starts out like a gramophone record. There's a nebula, a great disk of gas around the sun. There's all huge amounts of collisions, and eventually it all settles down. And George Weatherall did show you could actually get 4 terrestrial planets, but really not much beyond that. In fact, the planets Neptune and Uranus shouldn't even exist. But there is a price you pay for getting 4 planets in the inner solar system. That is that they're all made of the same material. They're all homogeneous. And so the model, unfortunately, doesn't have the inbuilt capacity to explain the chemical differences between the planets. And that's why the disk boys draw a lot of attention to the importance of collisions. But basically, you've got like Saturn's rings. Everything's sort of the same. And the way you get around this is they have these massive collisions. They propose that in one stage the Earth got hit by a Mars-sized body at a huge speed. But where the heck did that Mars-sized body come from? It's a case of putting the cart before the horse, or encountering a sort of a dog being wagged by its tail. Everything is sort of topsy-turvy with the disk boys. And that I think it's just creating an extra sort of nightmare to explain a deficiency in the theory. And that's always been a problem. In the case of Mercury, for example, they claim that Mercury once formed with I might have mentioned earlier, Mercury is very iron-rich. Perhaps I didn't, but up to something like 70% of its mass is iron, and then it's surrounded by a silicate layer. Well, according to the disk theory, Mercury started out like the Earth, or a terrestrial type of object, with a much thicker mantle of silicates. And then Mercury itself got clobbered by another planet, and it blasted off its silicate mantle. So, although Mercury initially started out with 30% of iron and 70% of silicate, most of the silicate got blasted away to leave just the iron core. But where is that other planet today? And Mercury, if that ever did happen, it would bear testimony of that deed so long ago, and you'd expect Mercury to have a wholly glazed surface, like a billiard ball. The Mercury's surface is one of the things that was most astounding, one of those first Viking shots, because its surface is just like the moon. It's ancient and cratered. There's no evidence anywhere there of widespread melting. The mercury is just accumulated from myriads of smaller objects. So collisions are not the way to go. And then you, of course, as I mentioned, not only we have our own planetary system, but spread right throughout our own solar system. There are at least 4 other examples of miniature planetary systems that the Voyager spacecraft visited in the 1970s and 80s, the Jupiter system and the Saturnian system. They're just like replicas of miniature planetary systems. The Galilean system is a prime example of that, and I got very involved with the Galilean mission to Jupiter over the last 7 years. I'll talk a little bit about that as well. But the moons of Jupiter are small compared to that gas giant, and there's Ganymede. They're as small compared to Jupiter as the planets are compared to the Sun. And there are many similarities, differences of chemical composition. Europa's surrounded with a sort of an icy shield, possibly an ocean down there. Io, which is volcanically active, Ganymede out there. And the Galileo mission has really confirmed beyond a shadow of a doubt that each of those Galilean moons has got its own story to tell, and almost certainly they must have formed it by a very similar sort of process. So I think that's the upshot, and we'll come back to that Galileo mission. Here is a sort of montage you see. It shows how big Jupiter's red spot is compared. There's a nice Galileo image of Europa. And Io, of course, and Ganymede, the largest natural satellite in the solar system. So it's an extraordinary planet. Saturn is another planet. It's the land of Isis. Its moons are very small compared to that planet. I think that's Enceladus and Tethys and Dione. And next year is going to be quite exciting because the Cassini probe will arrive at Jupiter and go into orbit about that planet and measure up all the properties of its rings, like a giant gramophone record, and beyond it, its moons. The moons are quite mysterious because they don't show quite the same uniform trend in densities as seen amongst the Galilean satellites of Jupiter, and so obviously some other forces have been at work. And over the next year, I hope to gear up and get ready for that sort of Cassini mission. It'll be NASA's last big multi-billion dollar mission that's been planned. All the missions beyond that are going to be short. The little Dan Goldman jobs, little 200 faster, quicker, cheaper, or something like that missions. But the Cassini was the last of the big ones, so I'm very keen to go out with a bang on that one. It'll be 2008 when I get my last paycheck from Monash, I suppose. I've survived that long. And so I've survived the Galilean mission. Galileo, I hope to survive the Cassini one as well, for her to go into orbit herself. That's not a very good slide. So how did the solar system form? Well, almost certainly it must have formed from one of these interstellar gas clouds that you see out there, and those dark lanes of gas and dust. But we're not quite sure of the mechanisms which lead to the final result. But we do know there's a lot of new information from all these different, the Hubble telescope and other new telescopes with measuring properties of these dust clouds that get it penetrate inside them. And undoubtedly over the next 10 to 15 years, we will in fact uncover the workings that are going on inside these clouds of gas from which stars are formed. The great complexes of that gas that evaporate and leave behind these sort of very young stars. And we need to be able to sort of peer inside those to sort of see what's happening. And so there's a lot of sort of physics and so on happening at the edge of this cloud, and then you get left behind these sort of proto-stars. That's the Cone Nebula. I think that was one that was released earlier this year. I'll just sharpen it up a bit there. And again, it's a region where a lot of young stars are forming. So it's believed that somehow if you look into one of these edge-on discs of gas and dust, there's a great cocoon of dust, and you can't really see inside, and you can get a perhaps slight glimpse of the star that's there. but you can't sort of see the inner workings of whether or not the cloud is actually throwing off rings of gas. And so I'm hoping one day that I'll actually capture one of these clouds in the process of throwing off a gas ring, and in particular to investigate this process of supersonic turbulence, which I believe was responsible for the sun shedding these gas rings. So what happened in the beginning, the sun was probably a great, huge cloud of gas which contracted inwards from a great size, and as it grew smaller, as I said, it sped up and cast off these gas rings. Now, the reason it cast off gas rings was probably because of this mechanism of supersonic turbulence. The primitive sun was probably once very active inside. And when I went to Oxford in the late 1960s, my mentor, Dirk Tahar, suggested really turbulence was probably the mechanism. And Tahar, he was a Dutch fellow, but he was the one who really got me interested in how the solar system formed. And as you can see, rather sadly, he died about a year ago, and I did, in fact, earlier this year, I went across to Britain. They had a special memorial service for him, and I did give a couple of lectures in London and in Oxford, and also I published a special paper in the Royal Astronomical Society in May as a sort of tribute to Tahar's contribution. And it was he who really suggested to me that turbulence played an important role. And we have published several papers together on that. I'll show you one of those later on. But basically what we're proposing is that not only do you have gas pressure inside the sun when it formed, but there's also turbulent pressure. And this turbulent pressure arises from very active sort of convection that's taking place inside the clouds. It was a sort of very fierce sort of cauldron with rising and falling columns of gas, and we're proposing that the convective currents or thermals are moving with many times the speed of sound, up to 5 times the speed of sound, and this creates a turbulent stress, which is the square of that. There's about 35, 5 or 6 brings you up to there, and it's because of this turbulent pressure which we believe that the sun shed these gas rings. And it's hard to sort of visualise that. I got Charles Morgan once did knock up a slide for me when he was in Japan to try to convince one of the locals there to try and draw what the turbulent sun would look like, and there were these great sort of flares. But it's not quite right, because I don't think the flares were meant to come out of this altogether. And I wasn't able to speak directly with the artist myself because I don't speak Japanese. I think I might have got mixed up with the sort of the panspermia theory out here as well. I think he's doing another article for a biologist, and somehow got the diagrams and them together. I'm not quite sure. I'll have to speak to Charles. Needless to say, in 1973, it can't be said that there was a stampede of admirers of my work. In fact, this was a criticism that was made by one of the referees of the astronomical journal, astrophysical journal. Al Cameron said when it became apparent that supersonic turbulence was an assumption of the model, he quit. He couldn't see any way this paper could be published. It was a bit disappointing. It took me 10 attempts to get the turbulence theory paper published. Eventually I did get it got published in Europe. And just recently, as I said, in May, we did with a student called Chris Dite, we published our first numerical simulation of supersonic turbulence, proving beyond the shadow of doubt that supersonic turbulence does exist, and it does lead to the sort of properties that Laplace had sought 200 years ago. We still have many more simulations to do, but in fact, this paper is a very important paper, and I think it will be a benchmark in the years to come. The turbulence, when it put it into the cloud, it makes the outer layers expand to a great distance, and it actually endows the cloud with all the properties needed to shed a gas ring. What's called the moment of inertia of the cloud drastically declines, and to a very small value, and this enables the cloud to get rid of very little mass. As it contracts in from the orbit of Neptune, it only has to shed a very small amount of mass to remain rotationally stable. And that's why the masses of the planets are so small. because the sun was able to efficiently get rid of its angular momentum as a result of having this very low moment of inertia. And the formula for that we could meet later on. You also get a huge increase in the density at the edge of the cloud, and the cloud actually is able to store a great lid of material at its edge. And it's because it stores this great lid of material, it actually seeks to abandon its angular momentum not in a continuous manner, but in discrete amounts. It drops off its first gas ring at the orbit of Neptune, and then the interior of the cloud has to recover equilibrium again and create a new lid of material. And the process of extruding new material to the surface from the deep interior to build a new lid actually slows down the rotation rate of the cloud and becomes stable again. And it doesn't want to throw off any more gas rings till it gets to the orbit of Uranus. And I have actually a movie showing this, and well, I didn't bring it along tonight, but I did have a student last year or the year before from the IT department who created this movie showing the cloud contracting inwards and throwing off this. These are the gas rings seen side on. So we're almost 100% certain now that the primitive sun really did in fact abandon these discrete rings of gas, and just as Laplace had suggested. And it all comes about as a result of supersonic turbulence. I haven't got time to go into the mechanics of all these gas rings. They're in a state of differential motion. The inner parts of the gas move slower than or actually more rapidly than the local Keplerian speed, and the outer regions move more swiftly, or at least the other way around. I've got it back to front. And these are slow-moving gases, and these are fast ones. But once the material condenses from the gas, any solids have to move outwards if they're coming from the inside, and the ones from the outside move in. You can actually prove you do get a concentrated torus. So let's have why each planet has been focused into well-defined orbits. And the outer planets formed first, and Jupiter formed ahead of the asteroids, and therefore it wasn't really fair. The poor asteroids would have formed a planet if it hadn't been for Jupiter, but Jupiter sort of prowled around the sort of the chicken yard while these asteroids were trying to form a planet, making growling noises and frightening the dickens out of them, really. And they just completely freaked out, just couldn't form a planet. Very nasty experience for a little person. And Mars also is only a tenth of what it should have been, all as a result of this very naughty fellow here, Jupiter. Beyond Jupiter, of course, I mentioned you come to the world of Pluto and Charon, which we haven't really visited. There is a spacecraft that will be launched there, I believe, a Pluto Express later on this decade. It won't cost that much to go there, and we'll visit. And I've made some predictions. These moons are absolutely loaded with carbon dioxide ice. And then in the asteroidal belt, there are amazing discoveries. This was a Galileo discovery of this moon called Ida. Had a tiny little satellite called, I think, Dactyl, only about 1,600 metres in diameter. And it means that the asteroids, when they formed in fairly sort of slow. The relative motions were quite small, and this allowed things like Dactyl to be captured into orbit. Had there been all these fierce collisions that you hear about on those BBC movies and the planets, then none of this would have happened. The condition that you can capture a moon like this is that the relative velocities were very small, and that's exactly the sort of scenario you get for gas rings. And because no one really believed in my ideas about supersonic turbulence, I sort of said, oh, well, I've got to go out of my way and see if I can test the theory. And as many of you know, over the last 25 years, I've made many predictions about what would be found out there, and a lot of these have in fact been borne out, just contrary to the expectation of my critics, who think I'm somewhat deranged. So it is rather unusual that a theory as mine is supposed to be so deficient is in fact able to make such very good, accurate predictions. And this is the formula that gives you the ratio of one planetary orbit to the next. That's the mass of the gas ring, that's the mass of the cloud, and little f is the moment of inertia. And if you make little f very small, like 0.01, which you can achieve with supersonic turbulence, it allows you to shed gas rings and have little m quite small to big M. So that's where that comes in. And I did use the theory, as you know, members of the ASV have probably been to many of my talks there in the 1980s, when I think the ASV thought highly of my work. They've been corrupted in a way by, had some rogue speakers from Swinburne and elsewhere who haven't properly, say no more. But so I did make some very valid predictions that can't actually be taken away there. They were published back in 1977, long before the planet Voyager actually got to that planet. So they are bona fide predictions, and also in the case of Neptune too, I did make a prediction that Voyager would find 4 new moons about that planet, and there's Triton, which orbits at about 15 radii, but there should have been 4 others between about 2 and 5 radii, and again, had trouble publishing this, but Charles managed to get it published in Japan just in time in a magazine called Newton, saying, according to this chap called Prentice, there should be 4 new moons of Neptune. And as you know, they did in fact, Voyager 2 did in fact discover those 4 moons within a few weeks of this being published. And this was the official photograph of the 4 moons. They're not visible from Earth, because that's Neptune in the middle, because they're all coal black. They're just very dark, and you just can't see them. So that's an amazing thing about this modern Laplacian theory. It is able to make a number of very good sort of predictions. Here are the, again, now that's talked about the ability to explain the orbits. We also have the other thing that in the last 10 years I've got interested in. I think I have given at least one other lecture to the Astronomical Society of Frankston, and then I've become very interested in the chemistry of the solar system, trying to explain the different compositions of the planets. One of the nice things that comes from this modern Laplacian theory is if the Sun did contract as a great cloud, cohesive cloud shedding gas rings, then the temperature at the edge of the cloud would vary inversely with its size. And this means that the more distant gas rings are shed off at lower temperatures, and there you'd expect ices to prevail. T goes as 1 over R. But as you come in towards the Sun, it gets warmer, and then you tend to get more rocky planets that form. And you can actually use the model to make detailed predictions for what you can compute the temperatures at which planets form. For example, Mercury would have formed at about 1600 degrees, and at that temperature it's so high that very few silicates can form, and Mercury consists mostly of metal. You can see it's 67% iron and nickel, compared to Earth or Venus, which is about 32.6. So the nice thing about the modern Laplacian theory is that each planet forms in situ, and it has a completely different chemistry. And you can use that diagram here to actually work out what each of the planets are made of. And in particular, the planet Mercury, as I just described a moment ago, and is probably formed at such a high temperature that only iron can condense in its gas ring. Iron has a higher condensation temperature than silicates, and silicates are only able to condense out of the gas close to the mean orbit of the gas ring, whereas iron can condense right throughout the gas ring, and there's a natural sort of fractionation process which allows iron to become more predominant. And that theory, that can't be produced. That phenomenon only occurs very weakly in the disk theories, and the problem with the disk theories is that even if there was an initial iron inhomogeneity at the orbit of Mercury, it would soon be swamped out by the addition of other material beyond the orbit of Mercury. And so what's happened now is there seems to be an overwhelming amount of evidence in favour of this gas ring model, but it just is not yet sort of quite widely appreciated. This shows you the composition of Mercury. And Ian, are you focusing it as well?
No, I'm not trying to. Will you do it?
I was having a go.
Yeah, so.
Look on yourself as the master focuser.
Yes, well.
Yeah, thanks, Ian.
No, that
Oh, very nice.
nice.
It's gone out of focus now. Yeah, that'll do.
Not very good weather.
Okay, well, what we can do, we'll probably leave it there.
No,
Is that right?
That's one better.
Yeah.
Yeah.
Yes. Probably I'm in the ideal position to do this because I had less to drink than Ian. I'm right at the front, and it's very hard from a distance to really get that focus. Anyway, the model predicts the composition. This is a model we presented to the IAU meeting in Sydney for Mercury with a student called Daniel. We predicted the internal structure parameter of Mercury, 0.325, and we hope that'll be measured in about 8 years' time. At the moment, we don't know what the relative size of the iron core is to the radius of the planet, but the modern Laplacian model gives you a precise estimate. And Venus, of course, is a very dry planet. It's shrouded in cloud and it's carbon dioxide, so it's very hot at the base. There's absolutely no water there at all. It's completely anhydrous, very little water vapour in the atmosphere. Whatever water vapour is in the atmosphere of Venus has come from comets, and a very inhospitable environment for it to be there at all. It's Earth, which is the hospitable planet to be, and the Earth's about the right sort of mass, and there's sort of plenty of water and stuff like that. We're just right close to the bay here. Though this is not Port Phillip Bay, I'm not sure what bay it is. I think there's a highway there. You could detect what side of the road those cars on, it's possibly somewhere. The Earth's water came from this mineral called tremolite, which forms at about 700 degrees. There's no water that can be incorporated as ice, but there are rocks that naturally contain water. And the initial Earth had quite a lot of water. But as the Earth heated up through radioactive decay of nuclides at the centre, and also the Earth's gravitational energy would have driven a lot of water into space. We're lucky that a little bit of it has survived to form our hydrosphere. But the nice thing about this model is that it does describe the densities of the planets, and you can see the Moon, as I said, probably formed from the Earth there. The Moon is made of very dry material. I don't think there's any water inside there at all. I think there's a spacecraft that the ESA people of the European Space Agency sent off last week. It's on its way to the Moon or somewhere. It's going to take a few months to get there, and it's on with an iron probe, and they hope to sort of measure much more about the Moon. Ian, is there any chance you could lift that carousel off and replace it with the second carousel? But I want to finish up in about 10 minutes or so because of the scheduled tea break. And
This one's empty.
I think Gillian
Right.
very kindly been looking after the second carousel. Very responsible person. And
Right.
you okay, Ian?
Yep.
Good work. Well done. And now, the thing about the Earth, it probably has a molten core. So the Earth is the first planet out from the Sun that's got a lot of iron sulfide at its centre. Iron sulfide melts at a low temperature, and I think the Earth's magnetic field has come from that. And we need that magnetic field to protect us from harmful cosmic rays and things like that that bombard the Earth's atmosphere. In fact, you have the beautiful auroras and so on that come, and shimmering light, and northern lights and southern lights. But if we wouldn't have those if it weren't for the Earth having this iron core. It's actually iron sulfide. Venus can't have an iron sulfide core because it formed at such a high temperature and iron sulfide couldn't form. Mars does have iron sulfide, and up till recently we thought it had all frozen out, but there's been some recent measurements suggesting that Mars may also have a small liquid layer at its edge, and that can't be iron, it has to be iron sulfide. So this sort of compositional model does seem to fit in well. And there you can see the Earth's magnetic field is protecting us from the solar wind, which is very harmful. But then, as a side effect, we do get these northern lights and southern lights, which would be nice to see one day. And then, of course, Mars there's another world in its own, and that's about to be bombarded with some spacecraft this summer, and we're all going to be looking at it, measuring what's inside it, and so on, and its internal structure. And we know, I'm pretty certain there's not a shred of evidence that, you know, there's some sort of bandicoot out there. I've looked around all of these rocks. Can't see any possible sort of a wombat tail. I don't know. Oh, there's a tree. There's a tree. Yeah. Well, that's actually one of Ian's detritus effects on the slide. There are no mushrooms. It's not. It's going to be a goner. And but Mars originally did have actually more potential water. You see, the Earth only had 10% of water, the water-bearing mineral, but this one's got 13. Mars has a huge amount of water inside. It was never massive enough to drive it out, and I believe there's a great probability, and there must be a lot of sub-Martian lagoons or great oceans of water there waiting to be discovered. So that yellow curve gives the density that comes from the modern Laplacian theory, and you can see how it actually does create a very nice fit to the curve. Now, at the edge of that slide, you might have seen Jupiter. So I want to finish up my talk talking about the Galilean mission. There's Jupiter. Galileo, of course, discovered the 4 moons of Jupiter in 1610, and amazing observations, and that's why the mission was named after him. It took off a long time ago, back in 1989. It took about 6 years to actually get to Jupiter because of the way they had to redesign the launch after the loss of the Columbia shuttle, and we've heard a lot about that in the news recently, this Vega mission. Why it took so long. It was rather lucky because I was able to visit the lab quite a few times during that period, and I was there when it arrived on the 7th of December 1995. It was a very exciting day when the spacecraft got to that planet, because a huge probe was released, and it actually went into the planet's atmosphere. It was released 6 months earlier. It's the orbiter, which over the last 8 years, the orbiter's been going around Jupiter and visiting all the moons, but it was on the very first day that the probe went into the planet and landed. It went right into the deep atmosphere, and there was a parachute that slowed it down and so on, and it measured all the gases. And we really didn't know anything at all what the gases were inside Jupiter's atmosphere. We knew there was hydrogen there, and methane had been detected. But as far as the other materials, we didn't know any of their proportions. For example, sulfur, there was thought to be about 20 parts per million. Yet according to my modern Laplacian theory, the amount of sulfur in Jupiter's atmosphere should have been at least twice the normal solar abundance. And I've done some very accurate calculations of what the solar abundances are from reconstructing meteorites, and I have a student, John Latangio, who's now a lecturer at Monash, who worked with me on that, and we realised many years ago that this is not the solar abundance of sulfur. The solar abundance of sulfur is about 37 parts, and that's in the sun, and therefore I predicted the sulfur abundance would be twice solar, which would bring it up to about 74. And the reason for that is that the moons of Jupiter, if they were made of solar material, Ganymede should have 40 parts of rock to 60 parts of water, but actually it's 50-50. And so Ganymede somehow has, Jupiter's atmosphere is somehow enriched in heavy elements relative to water. And I worked it out that enrichment was a factor of 2, and therefore, if the modern Laplacian theory is correct, the amount of sulfur in Jupiter's atmosphere should be about 74 parts per million. But and it was not until about May of 1996 that the result was released. That was my prediction of 74 parts per million, and the observed value from the probe was 77 plus or minus 5, which does include that number. In fact, it's a bullseye, and the chances of just getting it randomly was less than 1 in a billion. So it was a very significant triumph of this modern Laplacian theory. and no one else, I think, made any predictions like that at all. And that result still stands. They did a reanalysis and published it again in May of this year, this result. So this is one of my results that is sort of locked in, and no one can sort of take it from me. It's a very, very valuable sort of achievement. Things that I've lost in my lifetime include, I had a very nice 1972 Ford Fielder. This got relocated at my wife's instructions to the springy tip about 3 years ago. There's only one window left working on it. The motor was magnificent, but when I was at a conference, I think she had the opportunity to call up the RACV and say there was an unroadworthy vehicle right outside our home. Almost like that. Very sad end to an old friend. Ian wouldn't allow me to travel in his vehicle tonight. I'm not sure whether that was because his windows aren't working, I don't know. So Jacob showed me the way. This is the Galileo probe orbiter, which has just finished up. I used my theory to predict the composition of the Galilean moons. Heale, of course, was discovered by the early 1970s, at least by 79, to have a volcanic. It's in a tidally. This moon has been tidally distorted in its motion around Jupiter. It's in an eccentric orbit, and every now and then you get a volcano belching out of it. And it's the only sort of volcanically active satellite, I think, in the solar system, at least at this level. But not only is it spewing out sulfur, but also they found recently a lot of chlorine as well, or sodium chloride. And that's one of the things in my model. I did predict there'd be quite a store of sodium chloride inside that moon, which means this is a so-called sodium cloud that's coming out of Io. Europa is a moon that was a mystery by the Voyager project. The Galileo project has sharpened up our images of the moon. It's a moon that looks like a billiard ball, and once it was in fact entirely, it was complete ocean there, and in my theory this ocean would have been 160 kilometres deep. It was water that was driven out from the deep interior of the moon, from breaking down of hydrosilicates. And the Galileo spacecraft took close views and showed, in fact, there must have been an ocean because of all these sort of icebergs and so on that had formed and frozen. It's not clear whether there's any water still down there now. I believe it may actually be all frozen, but some people are holding out hope that, in fact, it is an ocean down there. Again, I used my theory to predict the moment of inertia factor of the moon. I was getting pretty desperate at that stage. I thought I'd go up to the third figure and make it 0.347. That's sort of an act of a desperado. But anyway, Galileo in 1997 went by and found it was exactly 0.347. Of course, those boys have a bigger error bar than me. I worked at very high standards out of Monash. I'm trying to train up the NASA boys to. No, anyway, what's happened? They had about 4 main passes of Europa, and I think the final answer is 0.346. But I was within a quarter of an error bar, so it was a very significant achievement. And I don't think anyone else has come anywhere near the sort of the level of success that I've enjoyed with these predictions. It's not clear whether it's frozen there or whether there may be water down there, and it will need another probe called the Europa orbiter to go to that planet to work that out. There's Ganymede, which is the largest natural satellite in the solar system. It's probably completely differentiated, and it's got an iron sulfide core and a rocky mantle and probably a frozen layer of ice. And Callisto is the outermost Galilean moon, which is a great sort of frozen snowball. And in fact, I did predict that that would be very uniform inside and magnetically inert. It's got a lot of ammonia ice that would have formed there, which would have made the ice very, very soft and easy to convect. And I did predict that it would be chemically uniform and inert. In fact, that was sort of confirmed as well by Galileo. So on the basis of this modern Laplacian theory, I did make a number of predictions with the mission, including the fact it's pretty well homogeneous. More recent measurements have shown it probably does have an icy crust at its surface, but more importantly, it may have an ocean just beneath the surface, about 100 kilometres down. It can't be normal water because that would be totally frozen. The only way it can be an ocean if it's made of ammonia, and that's one of the things I had predicted about 20 years ago with Heale, that there would be ammonia inside that moon. And this slide, I push these upside down, but it does show the...
Do you want to go one back and I'll flip it over?
That's very good of you, Ian. I could back up a notch. If you can just grab it by the throat, whatever the official anatomical section is on the slide.
And then I drop it back in the slot.
Only rotate it around.
And then you go
the
forward again, then go back.
Yeah, we'll go back. We can give it several shots if you like.
No, give it a go now.
Oh, well done, Ian. Yes, yeah, very talented fellow. Now, there's a tiny little layer where the temperature of the satellite exceeds the melting temperature of ammonia ice, and you would expect a little layer of melt. And that's another theory that seems to be borne out. The only thing that's a bit odd about the Galilean system, and Heale and I recognised this 20 years ago, is a little Amalthea. It's far too small compared to the other moons to be a Galilean moon. It's actually been drawn 10 times bigger than it really is. And if Amalthea was there should have been another moon in between. This is at about 2 radii, or 2.5, and Eo's at about 5.9. There should have been one in about 3.7. There isn't. And so we came to the conclusion that Amalthea is an interloper, and actually is a captured asteroid. And we published this in Nature magazine in 1979. There's Heale and myself, and this paragraph down here is the important one. I'll just blow it up a little bit so people in the back row can see. Well, there's Heale again, actually. It is possible that this tiny satellite Amalthea did form from a ring near 2.5, but the more likely, it's more like possible there is a captured stray asteroid. And in late last year, the Galileo probe did go by Amalthea, and it did actually measure up its mass, and it found out it was really just a rubble pile, or just a mixture of rock with some ice, and it didn't have any of the iron that you'd expect to be in it had it formed in Jupiter's orbit like Io would have had an iron core. So the Galileo did conclude it must in fact have been an asteroid. So that was a nice sort of final prediction we did make with that mission. And little Amalthea probably formed in the same orbit as Jupiter as what's called a Trojan asteroid, and these Trojan asteroids, they're made mostly of rock but with some ice, and they've got about 30% water and 60% rock. And Jupiter's core was made up of lots of little Amaltheas, but 2 or 3 strays were left over, and this one seems to have been captured after it formed. So it's more certainly it is a stray asteroid, and that's the sort of composition. At one stage we thought it actually might have been a stray C-type asteroid. It would have been much denser than that, but its real density suggests it probably was down at this level where it's got some ice. So the Galilean system has proved to be a miniature planetary system, and it is amazing that its properties are those that you'd expect from this theory. So the question is, are we alone in the universe? I think the answer is probably no. Here's a bit of a comic that I sort of tarted up for Open Day last year again. There's a picture of you in one of these. There's some people looking out there. And this space rocket's going through space, and oh gee, there are lots of Earths everywhere. But it's obviously you wouldn't expect the cosmos to be like that. Maybe these are Chinese boys. And did you say, when Peter say that it was a launch today of a Chinese rocket? Yeah. But that surely would be an Earth-bound rocket. I mean, I don't think they'd be going off into search of other planets. So I think we should come back, as Ian did the Monday last week, and went down and gathered at Mordialloc or somewhere to look at the marvellous occultation of Mars with the Moon. And it is, I think our own solar system has got so many wonderful, attractive features about it that will keep us occupied for many more years to come and give us good reason more to sort of continue enjoying astronomy and the world that we live in. So I'm going to stop there at the end of the talk.
Sure, Andrew would be open to any questions. Any 5 minutes of questions?
Yeah.
When you're looking at all the different elements,
Yeah.
you conceivably looked at a common element that actually runs through maybe Mars through to Pluto.
Yes.
Would it be ferrous oxide or something?
Oh, okay, good point, yeah. I didn't really, I did gloss over that a bit. Those gas rings that I talked about, and I should have, I'll do for my next talk, they do consist mostly of hydrogen and helium. That makes about 98% of their mass, and that's uncondensing. And as the gas ring is left behind by the sun at a temperature of, say, 500 degrees, it cools down to that point rather, having come from inside the sun. And all of the materials that can condense out at 500 degrees will form. That means things like ice can't form. So you are right, when you're looking for a substance that can commonly condense right throughout the solar system, well, that substance would be iron, because there's a lot of iron in the orbit of Mercury, and there's even iron in the orbit in Mars. 6% of Mars is made up of pure iron. But as you correctly pointed out, a lot of the iron has been turned into a ferrous form, because when Mars formed at a temperature of about, maybe I think it was about 400 degrees, there was a lot of water vapour around, and although water couldn't condense, the water vapour could react with a lot of the native iron and rust it out and form things like fayalite and so on. So Mars does contain some native iron, but much of the native iron of Mars has been rusted out. The Earth can't rust any iron, all it can do is form iron sulfide and iron. And so that iron is a material that runs right through the system, so would aluminium. But if you look at volatile materials like ammonia, that probably would first condense at the orbit of Jupiter, and maybe, as I mentioned, Callisto has got some ammonia. But the moons interior to the orbit of Callisto formed at progressively warmer temperatures. Those moons would contain water, and then they'd all contain iron as well, like Heale has got iron. So I should have had a slide. It's a deficiency in my talk. I probably lost a brownie point, showing me what the original chemical composition of the ring was. 98% is hydrogen and helium, which can't form a solid, and then there's 1.5% of that material forms ices, water, ammonia, and methane, and 1/2% of the gas ring is rocks and metal, and those metals are the ones that are common to all of the planets. So that's a very good question. Yeah.
Bruce? Andrew, you mentioned that animal theory was rubble.
Yes.
Could that satellite have been a comet rather than an asteroid?
Yeah, I mean, it was captured. You're right. No, you couldn't really. All that we really did, we just called it a captured asteroid. But if it was a comet, then you think it's probably the remnant of a comet, because all of the volatiles of the comet would have driven over. I suppose there's no reason why it couldn't be a comet, except we now, I think, in the old days, people were quite frightened of comets. They were considered to be quite massive, and many times larger than little Tanya's Hill's infant. Is that the 8 kilogram one? Comets were greatly feared, but we now realise from that nucleuses of them are quite small. But Amalthea actually is quite a big fellow. Its long axis is something like 270 kilometres, and it's typical of the size of a Trojan asteroid. They're typically in the range 200 up to 400. So probably if you take into account the size of Amalthea as well as its odd composition, it's more likely to have been a captured Trojan than a captured comet. But that's a good point, Bruce. There may well be remnant, well, we know there's something called Tholen, or there are some funny, there's something between the orbit of Saturn and Uranus that shouldn't be there. Maybe that's an old comet. Yeah, an old Fairlane or something. Ian?
Yeah, just a quick one about the density. The Earth's density overall is about 5.5. But the Earth's crust is less than 3, like 2.7 or something like that.
Yeah.
And I've heard it said, maybe erroneously, that the core of the Earth must have a density of greater than 5.5 in order, obviously, to, well, I suppose that stands to reason. It has to be greater. To make the overall density 5.5, it has to be greater. Now, in the case of Mercury, it doesn't have this low density crust. So you'd expect Mercury's density to be greater than Earth's, and it's not.
Yeah, it's probably something I can't explain in a short while, but what Ian has alluded to is that a planet's density, and depends not on what he's saying, it not only depends on the composition of the material, but also depends on the size of the planet, because the Earth is so large, it enjoys a lot of natural compression through its own gravity. And the density at the centre of the Earth is maybe up to about 11 times that of water, and it's probably pure iron. And if you move out from the centre of the Earth, you go out to about the 15% mass point, and I think that at that stage, or a bit further than that, you've actually come to the edge of the iron core, and then in my model, the next 10% is iron sulfide, which is probably molten. But when you come to the crust of the Earth, that's pretty well free of all iron. If you were to take one of the, I forgot your name, that first question, if you were to take all of the rock,
come you're not secretary anymore, Sally?
Oh, I left the committee quite some time ago.
Yeah, no. How come?
Well, funnily enough, I have no husband anymore.
Yeah, I'm aware of that.
So, yeah, I sort of, it was hard
That
to
shouldn't
get
be
to
a
meetings.
reason for leaving the committee.
Well, I had trouble getting to meetings and that sort of thing with the kids. But things have settled down now, and yeah, I can honestly get out when I want to. And so that was the main reason. Yeah. Yes, and as you can see, there's a happy face here too.
Oh.
Much less stressed, I can tell you.
Much less stress.
Yes.
Oh.
I might take up. Oh, hello.
A little later, is it?
The talk is.
Oh, that's right.
Actually, oh, you didn't bring it. You did. Oh, good boy. For you, has that got the video on it?
Oh,
Of the Mars moon that you took?
no,
Oh.
no. Sorry.
Brilliant.
No, I didn't think about that.
Oh, okay. All right. Well, we'll save Jane because she was treasurer as well tonight.
Does she? No, no.
Yeah.
I'm going to be getting all this stuff to leaders.
I was going to say, where are you going? Oh,
Probably just Heale at the moment.
oh no. Can't we go to that chalet that that guy owns?
Oh, here we go. Huge moon. There you go, buddy.
What's going on?
How you been?
Alright, good.
That's right.
Mate,
Oh,
Dave's really happy to hear
I had
now.
a presentation organised for the Leonids to do after the talk tonight, and I was doing some last minute stuff on it this afternoon. I kind of fucked something up and lost the light. I was been racing around, and then I left my friend out at the factory at work, so he's been down in bloody Seaford before I came here. It's just been absolutely just. I was going to come, but I know I better just make the last minute.
So is he a new member? This guy? The one that's got his chalet place?
I don't know. I don't know who you're talking about, honestly.
Oh, it's on the NAM in Yahoo.
Yeah, I haven't.
Yesterday.
Oh.
You haven't logged on.
No, I haven't been on the scent for a while.
Oh, well, they were talking about Heath at Wilson's Prom.
Yeah.
I don't know if you've got to.
No, not there again. I'm going to get it again.
No, I know. And this guy came on and said that he's bought this hotel coffee place at Mount Beauty, just in Fall Creek, and we're welcome to use free accommodation there.
Okay. I haven't read that one. I haven't read that one. Pretty good. Oh, well, just have a little. Yeah.
It's not too far, right?
It'd be good to do the elevation as well. It's a bit higher. It's going to be brilliant.
So I might go to that one.
I've got the day, so it's been pretty good this year, actually.
13. That's a Wednesday or a Thursday though. So you're going to take time off work?
Yeah.
Oh God, that means I'll. Okay. Alright.
Perfect. Perfect.
So how long would you go up for?
I don't know. What did you say? It was a Wednesday night, Thursday morning?
Yeah, I'm
Probably.
sure.
Probably 2 days or 3 days at the most.
Oh, so you won't go for the weekend as well?
No, because there's nothing on over the weekend until the 19th, which is like 6 days, which I think is a Saturday night anyway. So Wednesday, next Monday night,
Right,
I think.
okay. So Wednesday, Thursday, Friday. Alright. Okay, well let me know, because I'd like to go to that one.
Yeah.
Certainly want to go up closer.
Yeah, well the prediction is pretty good, so we should see some pretty good stuff. Like,
So no alcohol on this one, is that what you're saying?
right. What are you talking about? Which trip are you going on?
Okay.
You would buy yourself somewhere, some show, no alcohol going on, please.
Well, Richard said something about the schnapps.
Oh, yeah.
And this guy said, oh, sorry, no schnapps, but you can have the free bed. You know, so, we just
I'm sure we can sort stuff.
BYO the rest. So that would be good.
before I went on, so did I give you a box of astronomy stuff? I can't remember if I did or not. When I come into your place.
I'll get the shed if it is.
Okay.
If you did give it to me, I'll look up the shed.
Okay, I'll look at the shed then. There's a box of like all the old county stuff.
Yeah, I think it's up the shed.
Shed.
Yeah.
Oh,
Alright.
thanks, buddy. Hey. Oh, really? It's just been a busy girl. Oh, no. Oh, yeah. Oh, it's good. Got the camera out, roast down the zone, and set it up. Just check that for an hour, so I didn't. But yeah, that was good. It's quite interesting. Didn't see none of us had like telescope and all that, which would have been good to have. Said it's bigger, but I took video camera. No, I didn't actually do it. I haven't done anything with it yet. No, just got it. Yeah, something's good. Oh, really?
Andrew was one of his teachers.
Oh, wow.
And so Peter's Steph's son, so he's at HAO in Observatory in the States. So when Andrew was around with his family, he came home to him.
This would be the coolest September.
It's very cool. Yeah.
Yeah. You get some heavy rains. You get a thunderstorm. Yeah, very heavy rain. In fact, the gutters in the street are blocked. There's a couple of houses up from us. Drained up the side of the road and the rock. A lot of water in the street. Rain, heavy. Sun came again.
Now, I'm going to retrieve my slides.
May need those again.
Yeah.
Oh, Marty, you turned up.
Yeah, finally.
Leonids. Right, okay. Make it snappy.
Oh, yeah, whenever it comes in, for the stones, put it in front of the handle.
So you have the several layers, isn't it?
Yeah.
You going to do the cover?
Not quite there yet.
No, very late.
Okay, well, let's begin. People will come in and out over the next few minutes. I don't think we're going to be able to do much about that. I think it's first of all, is about the graze of Mars that was done last Monday night, Tuesday morning. The planet Mars actually grazed along the northern limb of the Moon, and it was visible from our region. And for those who were at the last meeting, we mentioned that it was going to occur, and predictions were actually put up on the site, the Xcorpia site. And what I'll do is I'll show you some images that I took, and I'm sure Ian will show some that he took. Just screw this. So you can see what very modest equipment can actually do. Image. Show you this one. I showed you in hard copy form. This was Paul Taylor's one that he took with his digital camera of Mars, shown up there, and the box shows the part of Mars that was actually being seen at the time. This is just holding a digital camera up to the eyepiece and taking a snap. This is one that I showed very poor quality last time on paper, and you can see some of the dark markings actually do appear in the corresponding spots there, and with a bit of imagination you can make out the polar cap. Also from last time, this looks a little bit better. David Girling took that, and I'm assuming that was with David's 14-inch. He's not here at the moment. And a few dark markings. And Jason, who came last meeting, snapped that one with his 10-inch telescope, showing Cirrus Major over the southern cap. Aloysius' telescope took that one at one of the brightest nights of Mars, and a high magnification, that one. That's through his 7-inch. The crescent there was, it was using my digital camera, which I hadn't quite got the hang of, and the flash went off.
Same as on Tuesday morning.
And, yeah, that's right. And the flash must have reflected it off something and then come back down the telescope tube. And it was probably quite fortunate that it did, because I think the camera adjusted its colour balance based on that flash, and so you ended up with a nice orangey sort of looking Mars. However, when I take it through my telescope, it actually looks better through on the screen than it does actually up here. You see the colour balance is not quite right. It comes out as a pinky colour. Now these are raw images; these haven't been sort of played with in any way. But you can very clearly actually on the computer screen see some of the darker markings of Mars. There's more there taken a little bit later. You can sort of see like Y-shaped areas. Now, the right one. Right, so John Cleverdon actually very kindly prepared the prediction for the graze on Melway's, got Melway's permission for that, and we also let the ASV know, otherwise the ASV would have missed this entirely. And this was from roughly the Parkdale, Mordialloc area, going right up through the hills through Wandon Way. And if you're along that line, you were right on the graze line of Mars, actually passing on the centre of the planet Mars, grazing along the edge of the Moon. And a group of four of us, Ian Sullivan, myself, Jakob Bukowski and Greg Walton, who I think is still next door. Oh, over there. We were positioned down around Parkdale Way, just south of the line, so that we would see it. And I'll show you some images.
Peter, just before you go back to the map.
Yep.
Now, what about people north of the line? Tell them north of the line and south of the line. What would they see?
Right. If you were north of the line, you would see a total occultation. In other words, the planet itself. Sorry, if you were north of the line, you would have a miss.
Well,
yeah, you'll have a miss. Yep.
At the ASV meeting, I saw a video that somebody's taken off from St Kilda,
yep.
And I think 30% of Mars or so went behind the Moon.
I've got a couple of stills of that one to show you. And if you were south of the line, further down Peninsula Way, you would actually see it duck into the moon.
Yeah, I saw it disappear for about 10 minutes.
Yeah. I believe, Bruce, you saw it Mount Eliza Way?
Yeah, not far from here, and about 3/4 of it went behind the moon. You can still see a quarter of it.
But not the whole planet, not the whole planet.
No.
No.
Well, not at maximum, no.
No.
You can see it before and after.
Okay. So through my telescope, there's the moon. Give you an idea of the relative size of the planet compared to the moon.
What sort of scope you got there?
Oh, it's a 6-inch, and not a particularly good one at that.
Oh,
But as you can see, the relative size, to give you an idea of how much of a challenge Mars is even for a telescope compared to the moon. Now, again, through mine, this is digital camera. Mars is getting very close to the limb of the moon there. Getting even closer, extreme magnification. That was probably getting on for around magnification 600 on my 6-inch telescope, which you should never push beyond 300 maximum. So that's right at the absolute maximum. Now, getting a bit closer, and there it is grazing right along the edge there. And at about this time, I was actually videotaping it, and I got the videotape of it, but had massive equipment problems part of the way through. This is not with a digital camera, this was with an ordinary 100 ASA film, just through the eyepiece, just going snap. And you can see the real orange colour of it. These haven't been played with in any way. Real orange colour of Mars. And this back to digital images, Mars sort of going away from the moon there. So there's some of the images at 2:30 in the morning. The boys in blue actually turned up to see what all the commotion on Parkdale foreshore was, because we were actually in the car park on Parkdale foreshore, and Greg Walton obligingly distracted them with the 18-inch while we went across the road and robbed the house. And we couldn't get rid of them, yeah. And they kindly agreed to a couple of photographs that we could show. 2:30 in the morning. There's Trevor. Now the one that Jakob mentioned was Maurice Valenberti. Picked up our alert that it was coming, and he's got a pretty good setup, as you can see. And he took a movie, and some of the stills from the movie, you can see at the magnification involved, you're getting a very good image of Mars, and it grazes along the edge of the moon, and probably 15%, maybe 20% ducking into it there.
Yeah.
The stills here don't actually do justice to how much turbulence there was in the air for him. I don't recall it being that turbulent actually where we were on the foreshore. I think it was much calmer conditions. So he would have been, I suppose, inland looking.
Somebody said Cleverdon.
Yeah. Okay, well that's all from me. Did anyone else have anything?
I've got 5 slides here, my 10 slides here.
Yeah, do you want to show those now, Ian?
Yeah.
I'll have to get rid of yours, that's right.
Yep.
What, you'll go forward or what? Oh, here we are. Now, you don't get Mars a perfect circular disc. That's worse, isn't it? You don't get a perfect circular disc. That's about as good as we'll get. Yeah. I don't think we'll do any better than that. No.
There's a star there as well, then.
That's at the big. That's the first shot I got. Then I said we'll just go through the. Getting closer. Yeah. And it's about half. You can still see it.
Yeah.
Just. Coming out. That's it.
Where was that then?
Yes. That picture, that was just out of sky and telescope.
No, where were you located?
Well, Peter was
Down there at
Same
place.
About 600 metres or a kilometre south of Parker's Road.
Yeah,
No.
Parkers Road, yeah.
No.
500.
Yeah. Just while that image is there, that's a picture taken in 1956 with a 60-inch Mount Wilson reflector. So one of the best shots, one of the great shots anyway, of Mars, taken from Earth. Of course, doesn't compare with spacecraft photos, but that's the sort of picture. was taken with Kodachrome film back in 1956. Right, okay.
Thank you. Paul, do you want to say a few words now?
Yeah, I will. Let's move on to planning on running what we're calling a newbies night, only for new members. And I'm a reasonably new member, and what I thought was what my attraction to the ASF has been is I've been lucky enough to go onto the public meetings and have a look down some of the telescopes. I think anyone that's been a public night, have a look through Greg's 18-inch has just been fantastic. And I just think some of the nights we have here, like tonight's pretty heavy duty stuff. And excuse my snoring through some of this stuff, it's all pretty technical for me. I just like going out and having a look up at the sky, and I reckon that a lot of new members would also sort of become a bit more involved in the club if they did that sort of thing. And what I want to do is I just want to show people 6 items where they can, any night of the week, they can wheel a telescope outside, point it upwards, and say to their friends, that's whatever, 47 Decani, that crater on the moon's called this. That's what the newbie night's going to be about. It'll be just about a bunch of people like me fumbling around with probably binoculars, telescopes. We'll be looking at things like Bob Heale's Sky for the Month. We'll be trying to maybe pick out a star of that. I reckon that's fantastic. And you just like, the idiot's guide to the sky. That's what I want to do. Is so I want to be recruiting all new members, to be contacting them and harassing them to come along to Frankston Heights Primary School. It's across the road from my place. So I can load the telescope across the road there. We should have some solid ground we can set up at, and hopefully see some good stuff. But if I can, I'll try and recruit people that are experts, say on the moon. If we have a night where it's a full moon, I'll be tapping people on the shoulder. Anyone that knows about the moon can come along and maybe explain what the craters are or whatever, and maybe some planetary boffins. People come along and talk about things like Saturn. I think Saturn's going to be open after Christmas. And I reckon that anyone that joins the ASF, if we can show them Saturn through their own telescope, we'll have a member for life. And I just think that's what I'm trying to do. Just share what I've seen. It's been fantastic. I've had some great nights, the public nights and the school nights, with Dave's telescope and John as well. The guys just wheel their scopes around and say, oh, have a look at this. And it's great. I'd just love to be able to do that. So that's going to be my goal, is to get all our new members, young members, old members, whatever. And we'll call it the newbies night, and we're going to start pointing our telescopes up there and showing the new people how easy it is and what there is to see.
Thanks, Paul.
And that will be, the timing of it will be probably a Thursday night, just after pay night, so if it's washed out we can go to the pub. And I put it down for November, the week before this meeting, which will be 13th. So I will email, put it on the Scorpius, but it's Frankston Heights Primary School. And just look for a bunch of nerds standing in the middle of the oval with telescopes. That'll be us.
Fantastic. Thank you very much, Paul. Right, okay. Marty, you able to go quickly, or I'll hand over to Bob?
Bob will go first.
Go for it, Bob.
Okay.
And while Bob's setting up, I'll just point out that there's a very good chance of an aurora tonight at our latitude and tomorrow night. So there's a high alert at our latitude for tonight and tomorrow night. During the daytime today, spectacular aurorae was seen across Europe, down as far as Germany. Yes. So we may be lucky here at 38. We certainly have seen plenty of spectacular ones over the years down here, and tonight may be a good one.
Peter, could you mention about that laser pointer before we forget? The laser pointer. About 2 meetings ago, I handed a laser pointer just bought for the ASF to somebody who was going to use it for club purposes. Now, I can't remember who the person was. Can that person stand up? No? Does anybody know anything about that laser pointer? It was a slightly smaller one than the ones we normally use here, but it was a laser pointer. Anybody? I hand a laser pointer to anybody that will own up to that fact. I'll never do that again, not unless I've had witnesses and signed documents.
Peter, can you or someone recommend any places not too far away that are good for observing?
All you need is a dark view, even from Frankston. We see quite readily in Frankston. You just need a fairly dark view between the southwest to south to southeast. Well, you can't predict them that well. Any time, like it occurred during the daytime our time.
Thank you. Great pleasure visiting. Yeah. To come again.
Safe journey.
Okay. Over the next month, we've got the morning planets showing their true colours a bit better. Saturn they're both, Jupiter and Saturn, they're both going into a dark morning sky, relatively due north. Saturn's sort of hovering. Jupiter looks like going much higher. And that's about it there.
What's the time there, Bob?
4:34 a.m.
4:34 a.m.
Yep, standard time, not summertime yet. We don't want to rush it.
That's Jupiter, sorry, Saturn on the left.
Saturn, the yellow one.
Yeah.
Jupiter. Okay?
So they're both there.
Yes, they're
If you
both
get up
there.
at 5 in the morning, you can see both planets.
Yes, and clearly you'll see them higher later as we move into the Heale period.
So getting up towards the end of November, 20th and 11th, yeah.
And clearly Saturn is up.
10 degrees, yeah, oh yeah, right,
Quite.
okay. Don't have to wait till the end of November, right? Only a matter of just in the next few weeks.
Yep.
Yep.
So they're hitting the dark sky. As I said, 2/3 dark sky. That applies for the beginning of the viewing period. As you move to the end of the viewing period, it's clearly a darker morning sky.
Just one last thing, what about, is there going to be another occultation or close to it there?
I don't think so, no.
Just near, but not.
You mean that one there?
No, over that side. Over this side.
I don't think so.
Just,
and it's
over, where you got 27th to the 10th there.
Yeah.
Yeah, but on the right there. You see how close that is? Is that?
It's not.
They're not really close. They're not real close.
No. It's a bit of a shot in the dark there, actually. Okay. For what it's worth, Mercury is rising in the western sky, joining Venus. It's going quite high, and again, a 2/3 dark sky. So that could be a good sight for those Venus-Mercury addicts for the evening sky. A clear peninsula westerly horizon. Okay, and you better get in quick because Mars is fading and going smaller. I'd say around the end of this month, it's going to drop dramatically in brightness. So get in quick for Mars, okay? Dropping and fading. And there's no moon to impede any of it, okay? No moon in that area. Virtually due north, medium altitude, no moon. Rightio. And the usual chart for the month. I've said it all before, all the objects are easy. I would point out, as on Sky for the Month, there was a notice in Sky and Telescope that in the constellation Leo, which is a morning constellation now because it's containing Jupiter at its eastern end, there are asteroids that for the first time, for a long time, are close to each other. I don't know the exact details, but it's a very close positioning in the sky of quite a few asteroids.
5 asteroids.
5, yeah. So any of you who've got computer telescopes or computer software or charts, it's worth going for. It's claimed in Sky and Telescope that appearance will not be repeated until 2006, and may not even be as good as the one coming early next month, very early next month, November. And it doesn't last only momentarily, it's there for about a week or so.
What, these 5 asteroids doing what?
Just
Within the same...
Just being
in the same field. In the same field of the telescope.
Yeah. You know,
What's
being nice to
what sort of angular distance between...
I wouldn't have a clue.
Yeah.
No idea.
It's a low power field, they said.
In a what power?
A low power.
A low power field, 5 of them, but you'd need a pretty solid magnification, wouldn't you see?
I wouldn't think so.
A low power, what's a low power? 40 times?
They were not faint asteroids. And they mentioned a website to go to check it out.
It's in the Sky Telescope here, there's an article.
Yeah.
The recent
November.
subscribing Sky Telescope.
November issue.
So, go for it. Rightio. Just briefly, I'll point out 2 objects by contrast. 51 Pegasi, appropriate with Dr. Prentice talking about planets. 51 Pegasi is about there, and it's one of the stars that's known to have a planet near it. And by contrast, for medium apertures, a galaxy group there. Otherwise, please yourself, for example, that star there, Alpheratz, that's a multiple star. V means it's variable, that one there. Rigel coming up in Orion, a multiple star. Telescope, binoculars, go for it. They are easy. Similarly, the southern sky, there's no magic occurring here, except for it's all being good stuff. I'll show, with a bit of luck, the Spanish Dancer Galaxy area there for moderate apertures, and in Tucana, Beta Tucana, and an easy double for probably small telescopes. So just 2 little objects for each sky. There's the Milky Way, flat on its back, right across the eastern, western of the southern sky. So it's galaxy country up there, and get used to it. Okay. 4 objects, briefly done. Northern sky, 51 Pegasi, the star that I mentioned, I'll show it to you in a moment. That's a type G2 star, and I think our sun is G3. Anyone? Yes? No? Okay. In other words, it's similar to our sun. No response there. It's 50 light years from the Earth, and the actual planet that's supposedly around 51 Pegasi is 1.1 times the Sun in diameter, and in terms of mass of the Sun, it's 0.45 Jupiter masses. I don't know why Jupiter is used as a reference. Dr. Prentice could have assisted me there. And the orbital time for the planet going around 51 is 4.23 days. Okay, we'll show you that. It's nothing much. It's just a nice field. Okay, there's the western end of Pegasus, and there's 51 Pegasi there. Trust me, see? Okay, it's just a nice field, quite colourful, and if you blow it up with binoculars, it just looks a little bit pretty, but that's all. There's nothing else. A bit of a gap there, so the planet's probably in there creating havoc. That was a joke, never mind.
What's the line going through the...
That's just the western end of the constellation going up, just to give a reference. Okay? If you take that back to the binocular view, same line. Okay? All right. Now, in Cetus, there is a galaxy cluster, which is quite reasonable to look at. The reference basically is the variable Myra there. Cetus is this area. It's on sky for the month, and the area is just there. But this is for medium apertures. 6-inch or 8-inch telescopes could do this. And if we enlarge that with binoculars, we have a plus in that there's a double star there. separated, pink and blue, and with a large binocular that happens, the galaxies come up, and there you go, that's the brightest. It's elongated, it's very obvious in a 6-inch telescope, so Hartung says. There's one next to it that's more circular with a less bright core, and there's one to the right that's elongated slightly but no visible core. And I didn't have time to make that one up. Okay, and if we magnify that, and I'm very naughty, you get that in a telescope view. Okay, so last two objects. Now, Beta Tucana, this is such an easy double with a telescope, it's not funny. Okay, that's the end of Tucana. It belts up in that way. You can see it on Sky for the Month. Beta Tucana is that one there. Again, trust me. See? And you can see it's two identical blue stars. There's argument that they're not associated with each other because it's actually a multiple of 4 stars, and the distances from the Earth of each of them are not quite absolutely suggesting that it's a true system, that there's debate about it. And if you hit that with binoculars or a small telescope, it separates. There's supposed to be a magnitude 6 white star in the field. Maybe it's that, and there's a magnitude 13 star, but I didn't have time to throw that one in. And if you hit it with a small telescope, it does the obvious and splits nice and finely. And guess what? That's beta 1, that's beta 2. Beta 1 being the brighter. Their magnitude 4.8, they are almost identical, except one's brighter, 4.8, 4.3.
So they're the same age? They're the same age?
I've got no idea. They're the same spectral type, so they probably are the same age. Whether they're physically close together in space, no one seems to be quite sure. What was your question, Brent?
What's their separation?
I've got no idea. I just type it in and my programs take over. My programs. That's in a database that I've made up, and I don't look at it anymore because I don't have to. I'm bad. Okay. And lastly, the Spanish Dancer Galaxy in Dorado. That's the upper bit of Doradus that moves down to the large Magellanic Cloud. Okay, so Beta Dorado and all that up right there. The Spanish Dancer Galaxy is just in there with little binoculars. We start to see that extended, and lovely area coming up there with large binoculars. If I can put the glasses on and get a bit of focus, there we go. That's the Spanish Dancer Galaxy. That's quite bright. It's a spiral, but I haven't had time to put the spirals in. If you're really desperate about not being able to find those, there's a little tiny galaxy on the line joining the 2 bright stars. And there's a little bit of a cluster there that's quite nice. That seriously is very easy, and those should be easy to pick up. That's easy at 6-inch. There's no argument. And when you enlarge it, it falls away, and it sneaks up to the top. So the one before was better. So, one more thing, on the moon, on Sky for the Month, I'll be very, very brief. This thing on the moon that's on Sky for the Month, it's the with the moon to the unaided eye, it's the current position on the southerly chart, southwestern sky. It's the northeast bottom bit, the northeast bottom quarter. Sea of Crises. I'll turn it around the right way now. The compass directions are there. You've got a little reference thing. Sea of Crises, Endymion up there. I've put some notes on Sky and Telescope about 4 things. So I'll leave you to read it. They're easy things, and it's just a very small bit of the moon. Good fun. Radio.
So that's on the far left-hand side of the moon as you're seeing it in the sky.
Yes. Does the thing over there work?
As you see it in the telescope, to the top right.
Yeah, that's the way you see. It's a half moon, waxing first quarter. Okay, and your half moon is like that. Okay, this is a quarter of.
In binoculars.
Yes.
Yes.
Yeah, that's a quarter of a half moon, and I've just chosen 4 objects to talk about. Some craters, Sea of Crises, there's a deep one up there. They're on sky at the moment. You can look at it with binoculars, but really, to get the blow of that area, you need a telescope. Okay? And you don't have to restrict yourself to the ones I've mentioned. You've got that code, so go for it. And that's it.
I'll ask Marty to come down and tell you about the Leonids coming up and maybe the Orions. No, nothing on that? While he's setting up, I'll mention that the next meeting is actually the annual general meeting. It'll be a meeting like this, plus in addition the election of next year's committee. If anyone is interested in coming onto the committee of management, please see either myself or John Cleverdon, who has his hand in the air down there, and we'll gladly take your name. But nominations have to be in 7 days before the next meeting, so that's before November's meeting. And also, if anyone's interested in Astronomy 2004, they will be in by next meeting, so please bring your money along. The price has gone up, the recommended retail price has gone up to $22, but for members it'll be $20 only, so they'll be available next meeting. And one thing I was going to mention, but forgot to actually bring the details along, the ASV and the South Australia Society have got together to try and have a star party that they wish to start up as a tradition in the little desert of Victoria, sort of halfway between Adelaide and Melbourne. And they're calling it the South Vic Desert Spring Star Party. I think they're trying to have it as a tradition, much like Bastrop is. Unfortunately, I didn't bring along the date or the times or the contact details, but if anyone is interested, please contact me or any of the other members on committee, and we'll email the details to you or by telephone. Right, thanks, Marty. I'll put it on East Hawkers if you're on email. Go, Marty.
Just a quick little note to say that the Leonids for this year are coming up once again in the middle of November. A pretty spectacular meteor shower which occurs every year at the same time, middle of November. Myself and a few members here and a few members from the ASV have been observing this particular meteor shower about over the last 5 years or so with various results. But just give a really quick rundown on what the Leonids are if you haven't heard of them before. They're probably one of the best, or it is probably the best known meteor shower that occurs approximately every 33 years. And it was first probably written down or recorded in 1833 as a really major meteor shower or storm over the north of America. It was also the first time that a radiant was calculated for a meteor shower, the radiant being where the meteors tend to originate from a certain point in the sky. Let's see. Over the last couple hundred years, it was noted that the meteor shower returned every 33 years, and it started, predictions were started to be made about the return of this particular shower, and various results happened over those 33-year periods. As can be seen in 1899, there was no there was a meteor shower prediction, but nothing actually occurred. So that was a bit of a setback for astronomers at the time. And then in 1933, there was only mild activity. And then in 1966, another major storm occurred over the United States, which is really good. And then from 1966 until recently, predictions have got a lot better over the last probably 50 years or so. And over the last probably 7 years since the return of the meteor shower has occurred, there are various results that have happened. started observing them since 1988, where I was in Woomera. I saw quite a spectacular meteor shower then. The best one I saw was in 2001. We went to Alice Springs. We saw almost 3,500, about 3,000 meteors an hour for a period of about 2 hours. That was quite good. Okay. The Leonid meteor shower occurs when comet Tempel-Tuttle orbits around the Sun, has an orbital period of 33 years, and just so happens that during that 33 period orbit, it crosses the orbit of the Earth. So when the comet goes around the Sun, it leaves a trail of debris behind it, and then the Earth travels through that debris, and hence we have meteor showers. The particles go through the Earth's atmosphere. Just a quick little movie here that shows you sort of roughly how this happens. You can see the Earth following its orbital plane, and it goes through all the debris that's been left by the comet. And the direction that the debris tends to come from, or seems to come from, there's Leo on the right there. It's just the direction the Earth's going. The Earth's going towards Leo, the constellation of Leo, and so it appears that the meteors are coming from Leo itself as the Earth goes through that direction. As I mentioned before, the radiant is the area in the sky where the meteors tend to come from, or they appear to radiate from. As I said before, the Leonids come from, or tend to come, or appear to come from the constellation Leo. This is Leo here. That's the sickle of Leo, and the radiant is in the position just in the middle of the sickle here, and the meteors tend to radiate from that area of the sky there. Those arrows, they were actually plotted from a data that I took last year from video work that we did. You can see just if you travel all the arrows back to a point, they will end up in that circle there. To observe the Leonids or any meteor shower, you can use a tape recorder to record visual observations. It's pretty handy to have a deck chair or a banana lounge to lie down on so you can look up at the sky. It won't crank your neck all the time. Warm clothes are pretty important, especially during winter. Handy to have a bit of pen and paper, also camera, film, videotape. Sometimes I put a cord to keep yourself warm on the inside as well. Also very important, clear skies. Obviously without clear skies, as with most astronomical work, you pretty well won't see anything at all. With the cameras, it's quite easy to capture meteors on film. All you basically have to do is open the shutter up on your camera lens and leave it open for any period of time, up to maybe 10 or 15 minutes. And with a no meteor shower, you're almost guaranteed to probably get at least one meteor on film. And these shots here were taken in 2001 by various members, including myself, with various time limits from 5 minutes up to 15 minutes. We were getting up to like 15 to 20 meteors per photograph. What was the speed of the film?
Generally 400 ASA. It's a good medium, sort of. And if you're lucky enough, you'll get quite a large one, like 5 or these, which is captured. Okay, predictions have been made over the years by Dr. Robert Nord and his counterpart Asher. Also, a couple of gentlemen, Lytton and Nesson, Van Landert. They've been making predictions almost to the minute when meteor showers will occur in the sky, or peak meteor showers. Over the years, especially the last probably 2 or 3 years, they've got within probably 20 minutes of when these meteor showers will occur. So the predictions are really coming of age. So what we've got this year, not as good as previous years. As you can see in this plot here from Alice Springs, we were seeing up to almost 3,500 meteors an hour at its peak point. And that was generally, the prediction was only about 2,000, so it was better for us, as it turns out. Don't think they've got the numbers here. So the predictions were less in the numbers, but the time, I think they got within 7 minutes of the time.
So it's pretty well spot on. The best place in the world at that time actually happened to be Alice Springs or Central Australia.
Was it when 2000?
2001 this one was, yeah. So we're quite lucky. Usually Americans tend to get all the best meteor showers, so we sort of have one up on that here. So for the predictions this year, I'm generally on a rule the Leonids occur on the night of the 18th, morning of the 19th. But for the first time, the predictions actually have 4 different nights that the Leonids will peak at certain numbers. The top one is a stream that was laid down when the comet went round in 1499. And on November the 13th, which actually will be, the time up there is actually ET, so it will be 4:17 AM on the 14th, Melbourne time. We're going to be lucky nationally in Australia because we'll get about 120 meteors an hour of the Leonids on that morning, and it happens to be the best place. Melbourne has to be the best place to be this year for the Leonids. After that, there's a couple more times which actually, unfortunately, don't correspond to Melbourne time. One's 6:28 PM, 9 o'clock in the morning, and another one at 2 o'clock in the afternoon. But the rates on those ones are generally a little bit lower than what we should see. So really, it's probably a good chance to get out there, and if you've never observed a meteor storm before or meteor shower, there's a good chance that you'll see at least one a minute. And the predictions also suggest fireballs, a lot of fireballs, so really, really bright meteors this year as well. So the only unfortunate thing is that most of the dates are on weekdays. It's not too good in that sense, but if you can get time off, we'll maybe get up a couple of hours early one morning, especially on the morning of the 14th. Have a look outside, even if it's for an hour, and hopefully you'll see some pretty nice fireballs from the Leonids.
Marty,
yeah.
What's the reason that the first 2 dates are 6 or 7 days apart?
It's just if on the left-hand side there's the stream, the year that the stream was laid down by the comet.
So in 2001, the date was 18th and the 19th of November. So it only went through one.
They were different streams as well. One was 1866 when the comet laid that path, and I think it was 1767. It just so happens that the path of the comet also goes near Jupiter, or fairly close to Jupiter's path as well. And Jupiter tends to disrupt the different streams as it goes round as well. So there's no real correlation between the latest, let's say, a stream that was laid down maybe 33 years ago won't be near one that was laid down 66 years ago, and they won't be near one that was laid 99 years ago. They all get moved around a lot, so...
Okay.
Now that second one, that's 6:28 PM, because Leo wouldn't even be in the sky then, would it? Because it's the morning up here.
It is, yes. At the front, just near Don actually, I've got that sheet there. It actually rises, I've actually got what time it rises. Leo rises about 3 o'clock in the morning, 20 past 3. So for the top one as well, 4:17, Leo should be probably about 15-20 degrees above the horizon as well.
Yeah, but in the second one, well, are you likely to see anything from here?
Probably not, no. That's actually probably best for
somewhere.
North America is the best place for that. The other two I'm not really sure about, but the rates are only less than 10 per hour. But it's also interesting to note as well that the normal Leonids meteor shower, which occurs as like a background meteor shower, occurs every night on the 18th. That also has a rate of about 13 per hour, which is standard as well. That 13 per hour actually lasts for about 2 weeks, and the 18th is the centre point in that time. So about a week either side of the 18th, you'll see Leonid meteors as well, up to about 10 to 13 per hour. So you'll see them over the weekend, so you can probably get out there early enough. Yeah, that's about it. As I said over there, if you want to pick up the slip, just to give you an idea of the dates are, how many you might see. Yeah, have a look, see how you go. No problem, thank you.
Thanks, Marty. Maybe we can pass upon your next meeting to show some of those images that were captured last time of the Leonids and the Arrays, just to show what a storm looks like.
Okay, I've actually got it. See you, I can play with it.
Alright, well, what I'll do is I'll close the meeting, but I'll let Marty actually show this as we're departing. So thank you very much for coming this evening, and we'll meet here on the 3rd Wednesday of November, which will begin with the AGM and then on to the usual. Thank you.
Wednesday, that's the 19th. No, that's the 19th, so that's after this shower, isn't it? Right, the week after, yeah.
Leo is actually at this point just here. Just regular or something like that. Oh, okay, yeah.
Down there somewhere, so right through the especially when there's been not so much.
Ian, is it going to hand?
This gear,
astronomers well.
this is not project, this is ASF gear. No, we're still going to pack it up. Yeah, but it's not for my car.
Sorry.
Jakob, you disconnected. You possible starter on November 1st?
Oh, you didn't get my email on this now. No, not
Oh, well, you John, hang on, John Randall, you're the guy that I did get an email from somebody, it's you.
that weekend.
Yeah.
Long weekend.
Yeah, that's right, yes. It's going to upset things, but I mean, there's a function on that I have to go to on the 25th, and there's a wedding this Saturday, you see, so you know.
Couldn't put off 2 weeks.
No, next one will be the weekend, so yes, I happen to have
I've been confused, but I've been enjoying it.
Yeah, so last 6 months.
It would have been better the week before, right? I know.
Just the ones that paid.
It's disconnected.
Case.
Yeah, well, Mars is up fairly high. But then you put that bit down here, right there.
What have we got in there by any chance?
Well, if you look around, there's nothing brighter than Mars.
There's nothing there by
Anything's possible. Anything. I'll stand it up here. Put the case up here.
I can think of it if it's here.
This goes in there. It's the IR controller. Okay, open it up. That's the old one. Don't close it up again. This is going to be
was always the case when I got to class.
Don't pull the lens up like that. Where are you taking it out?
Because I'll put this thing there first.
You won't fit it. Right. But then this maybe they'll try that.
Does it go in a box by any chance?
Well, that's my box.
Right.
There was a box.
Okay.